National Electrical Code, or NEC, provides an exception for existing electrical installations where the service equipment has only a 2-pole, 200-amp disconnect. In this specific scenario, the ground wire is permitted to be run to the subpanel. This exception is rooted in the understanding that existing installations utilizing 2-pole disconnects have generally operated safely over extended periods. The grounding path established by the ground wire connected to the subpanel is deemed sufficient in these particular cases. However, for new construction projects, the NEC mandates that the ground wire must extend to the main breaker located within the service equipment. This requirement stems from the expectation that new installations should adhere to the most current and stringent safety standards. By running the ground wire directly to the main breaker, a more reliable and robust grounding path is ensured, thereby minimizing the potential for electrical hazards. It is crucial to remember that the subpole must be properly bonded to the service grounding system to ensure a continuous grounding path. The ground wire running from the pull panel to the subpanel must be appropriately sized, adhering to the NEC guidelines. In cases where an existing house is undergoing remodeling or expansion, it may become necessary to upgrade the service equipment to align with current code requirements. Although the NEC does permit an exception for existing installations equipped with 2-pole disconnects, adopting the best practice of running the ground wire to the main breaker in the service equipment is advisable for both new and existing installations. This approach guarantees the most dependable and secure grounding path. Now let's delve into specific aspects of grounding and bonding to provide a more comprehensive understanding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, allowing overcurrent devices, such as circuit breakers or fuses, to operate and clear the fault. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Article 250. Understanding these requirements is crucial for safe electrical installations. Grounding electrode system is a critical part of the grounding system. It consists of electrodes such as ground rods, ground rings, or metal underground water pipes. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage and provide a low impedance path for fault current. The size and type of grounding electrode depend on the size of the service and the soil conditions. Bonding jumpers are used to connect metal parts together to ensure electrical continuity. Bonding jumpers are required for metal conduits, metal enclosures, and other metal parts that are likely to become energized. The size of the bonding jumper depends on the size of the circuit conductors. Equipment grounding conductors, or EGs, are used to connect metal parts of electrical equipment to the grounding electrode system. EGs provide a path for fault current to return to the source, allowing overcurrent devices to operate. The size of the EGC depends on the size of the circuit conductors. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electric shock. GFCIs monitor the current flowing in the circuit and quickly disconnect the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. SPD diverts surge current to ground, preventing damage to sensitive electronic equipment. SPD are recommended for all electrical installations, especially those with sensitive electronic equipment. Now, let's discuss common grounding mistakes and how to avoid them. Firstly, improper grounding electrode selection is a common error. Using an inadequate or inappropriate grounding electrode can compromise the effectiveness of the grounding system. Ensure that the grounding electrode meets the requirements of the NEC and is suitable for the soil conditions. Secondly, incorrect bonding jumper size can cause problems. Using an undersized bonding jumper can result in a high impedance path for fault current, increasing the risk of electric shock. Ensure that the bonding jumper is sized correctly based on the size of the circuit conductors. Thirdly, failure to bond metal parts together is a frequent mistake. Failing to bond metal parts together can create a potential difference between them, increasing the risk of electric shock. Ensure that all metal parts are properly bonded together. Fourthly, improper installation of GFCIs is another common error. Installing GFCIs incorrectly can render them ineffective, leaving people unprotected from electric shock. Ensure that GFCIs are installed according to the manufacturer's instructions. Fifthly, neglecting surge protection is a problem. Failing to install surge protection devices can leave electrical equipment vulnerable to damage from voltage surges. Consider installing SPD to protect sensitive electronic equipment. Here are some best practices for grounding and bonding. Always follow the NEC requirements. The NEC provides detailed requirements for grounding and bonding. Understanding and following these requirements is crucial for safe electrical installations. Use quality grounding and bonding materials. Using quality materials ensures that the grounding and bonding system will perform reliably. Install grounding and bonding systems correctly. Proper installation is essential for the effectiveness of the grounding and bonding system. Inspect grounding and bonding systems regularly. Regular inspections can help to identify and correct any problems before they become hazards. Consult with a qualified electrician. If you are unsure about any aspect of grounding and bonding, consult with a qualified electrician. Let's consider some specific examples related to pool panel grounding. The NEC provides specific requirements for grounding and bonding of swimming pools in Article 680. These requirements are designed to protect people from electric shock hazards associated with swimming pools. The pool panel is a subpanel that supplies power to the pool equipment, such as the pump filter and heater. The pool panel must be grounded and bonded in accordance with the NEC requirements. The grounding electrode for the pool panel must be connected to the grounding electrode system for the building. This ensures that the pool panel is grounded to the earth, providing a low impedance path for fault current. All metal parts of the pool equipment, such as the pump, filter, and heater, must be bonded together. This includes the metal housings, metal conduits, and any other metal parts that are likely to become energized. The bonding conductors must be sized in accordance with the NEC requirements. A solid copper bonding conductor not smaller than 8 AWG must be used to bond the metal parts of the pool equipment together. This conductor must be continuous and unbroken. It is generally run around the perimeter of the pool and connected to all metal parts. An equipotential bonding grid is required for all permanently installed swimming pools. The equipotential bonding grid is a network of interconnected conductors that are installed under and around the pool. The purpose of the equipotential bonding grid is to create an area of equal electrical potential, reducing the risk of electric shock. The equipotential bonding grid must be connected to the grounding electrode system for the building. Ground fault circuit interrupters, or GFCIs, are required for all electrical outlets and equipment located within a certain distance of the pool. GFCIs protect people from electric shock by quickly disconnecting the power if a ground fault is detected. The NEC requires that all electrical equipment associated with the pool be listed and labeled. This ensures that the equipment has been tested and certified to meet safety standards. Regular inspections of the pool grounding and bonding system are essential to ensure that it is functioning properly. The inspection should be performed by a qualified electrician. Let's talk about upgrading electrical services in existing homes. When upgrading an electrical service in an existing home, it is important to consider the grounding and bonding system. The existing grounding and bonding system may need to be upgraded to meet current code requirements. If the existing service equipment has only a 2-pole, 200 amp disconnect, the ground wire may be run to the subpanel, as discussed earlier. However, it is always best practice to run the ground wire to the main breaker in the service equipment. This provides the most reliable and safe grounding path. When upgrading the service, it is important to ensure that the grounding electrode system is adequate. The grounding electrode system may need to be upgraded to meet current code requirements. All metal parts of the electrical system must be properly bonded together. This includes the metal conduits, metal enclosures, and any other metal parts that are likely to become energized. Ground fault circuit interrupters, or GFCIs, are required in many locations in existing homes, such as bathrooms, kitchens, and outdoor areas. When upgrading the service, it is important to ensure that GFCIs are installed in all required locations. Surge protection devices, or SPDs, are recommended for all electrical installations, especially those with sensitive electronic equipment. When upgrading the service, it is a good idea to consider installing a SPD to protect your electrical equipment from voltage surges. Always consult with a qualified electrician when upgrading an electrical service. A qualified electrician can assess the existing electrical system and determine the best way to upgrade it to meet current code requirements. Now let's delve into the nuances of service equipment and subpanels. Service equipment is the main electrical disconnect for a building. It typically includes the main breaker, meter, and other components. Subpanels are smaller panels that are fed from the service equipment. Subpanels are used to distribute power to different areas of the building. The service equipment must be grounded in accordance with the NEC requirements. The grounding electrode system must be connected to the service equipment. All metal parts of the service equipment must be bonded together. Subpanels must also be grounded in accordance with the NEC requirements. The grounding electrode system must be connected to the subpanel. All metal parts of the subpanel must be bonded together. The neutral conductor in a subpanel must be isolated from the ground conductor. This is to prevent neutral current from flowing on the ground conductor, which can create a shock hazard. The ground conductor in a subpanel must be connected to the grounding electrode system. This provides a path for fault current to return to the source, allowing overcurrent devices to operate. When installing a subpanel, it is important to ensure that it is properly sized for the load it will be serving. The subpanel must have sufficient capacity to handle the total current draw of all the circuits that will be connected to it. It is also important to ensure that the subpanel is installed in a safe location. The subpanel should be located in a dry, well-ventilated area. It should not be located in a damp or hazardous location. Now let's talk about bonding and its importance. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding is essential for electrical safety because it helps to prevent electric shock. When a fault occurs in an electrical system, current will flow through the path of least resistance. If the metal parts of the electrical system are not properly bonded together, the fault current may flow through a person who comes into contact with the metal parts. This can result in a serious or even fatal electric shock. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. Bonding also helps to reduce the risk of fire. When fault current flows through a high impedance path, it can generate heat. This heat can ignite nearby combustible materials, causing a fire. Bonding provides a lower impedance path for fault current, reducing the amount of heat generated. The NEC provides detailed requirements for bonding in Article 250. Understanding these requirements is crucial for safe electrical installations. Bonding jumpers are used to connect metal parts together. Bonding jumpers must be sized in accordance with the NEC requirements. The size of the bonding jumper depends on the size of the circuit conductors. Equipment grounding conductors, or EGs, are used to connect metal parts of electrical equipment to the grounding electrode system. EGC provide a path for fault current to return to the source, allowing overcurrent devices to operate. The size of the EGC depends on the size of the circuit conductors. Now let's discuss about the role of ground fault circuit interrupters. Ground fault circuit interrupters, GFCIs, are life-saving devices that protect people from electric shock. GFCIs monitor the current flowing in the circuit and quickly disconnect the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground. This can happen when a person comes into contact with a live wire and ground. GFCIs are designed to detect even small ground faults and quickly disconnect the power, preventing serious injury or death. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas. The NEC provides a list of locations where GFCIs are required. It is important to install GFCIs in all required locations to protect people from electric shock. GFCIs are available in several different types, including receptacles, circuit breakers, and portable GFCIs. Receptacle GFCIs are installed in place of standard electrical outlets. Circuit breaker GFCIs are installed in the electrical panel. Portable GFCIs can be plugged into any electrical outlet. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. GFCI should be tested regularly to ensure that they are functioning properly. To test a GFCI, press the test button on the GFCI. The GFCI should trip and disconnect the power. If the GFCI does not trip, it should be replaced. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. SPD diverts surge current to ground, preventing damage to sensitive electronic equipment. Voltage surges can be caused by lightning, power outages, and other events. Voltage surges can damage sensitive electronic equipment such as computers, televisions, and appliances. SPD are recommended for all electrical installations, especially those with sensitive electronic equipment. SPD are available in several different types, including whole house SPD and point-of-use SPD. Whole house SPD are installed at the service entrance of the building. Point-of-use SPD are plugged into electrical outlets. When selecting an SPD, it is important to choose one that is rated for the voltage and current of the electrical system. It is also important to choose an SPD that has a high surge current rating. When installing an SPD, it is important to follow the manufacturer's instructions carefully. SPD should be inspected regularly to ensure that they are functioning properly. In summary, grounding and bonding are critical aspects of electrical safety. Understanding the NEC requirements for grounding and bonding is essential for safe electrical installations. Proper grounding and bonding can help to prevent electric shock and fire. Remember to consult with a qualified electrician if you have any questions about grounding and bonding.